Oh, my pencil. Oh no, I haven't sharpened it yet. And it's already starting. I need to get my pencil sharpener. Got it. Hello everyone, it's January 14th. My cat almost ate my pencil yesterday. So I need to sharpen it again. Alright, what do we have today? Number of good paths. Maybe I've done this before. Yep, I've done this before. Holy crap. I don't remember at all. It's 2421, so I'll just say I think it's quite recent. It's a shame. I don't remember. There is a tree, okay? N nodes, 0 to minus 1. Ah, okay. You're given a zero-indexed integer array, vowels of length n, where vowels I denotes the value, okay? To the integer array, that is the edges. Undirected. A good path is a simple path that satisfies the following. The starting node and the ending node have the same value. I don't remember. All nodes between the starting node and the ending node have values less than or equal to. Now it starts to ring a bell. Okay. The starting node's value should be the maximum value along the path, including the last node. Return the number of distinct good paths. A path and its reverse are counted as the same path. For example, 0 to 1 is considered to be the same as 1 to 0. A single node is also considered. So all the single nodes are valid paths by default. So the first one, these are the values. So 0, 2, 3, that's one path. 3, 1, 2, 3 is another path. 1, 0, hold on, 1, 0, 2, 4. Yep. Wait, oh, this is not, because this one's larger. Come on, man. So every one, that's 1, 2, 3, 4, 5, plus 1, 6. Yeah, now I remember. I struggled with this one. 1, 1 is a path. 2, 2 is. Yeah, I seem to remember. 1, 2, 3, 4, 5, 6, 7. 5 good paths consist single node. 0 to 1 and 2 to 3. Okay. We have to redo this because I don't remember how I did it. Of course, we have to pick out the nodes that have the same value, right? And then once we pick out the nodes of the same value, we want to know how many paths are in them. And the path, it doesn't matter, we can always start from 1. And I'm going through everything because it's all connected. It's a connected tree. So we can start from 1. And then what? We're starting from 1 and find its children. Yeah, because it could be like all the paths starting with this root, right? Any tree, any subtree, we can say, if I know from this all the paths, that's what we want to know, right? All the paths except for single. Well, we can include single as well. Okay, so now to find all the paths starting with this, if we know all the paths starting with this, does that help? It has to be starting with this, right? Okay, all the good paths starting with the root. Now to find that, we can, keep traversing. And each one will have, if I keep traversing, and then once I found a path, the two are the same. And we need to make sure everything in between is smaller. Okay, so I start from a node, okay, and we have its value, and among all the children that have the value the children that have the value larger than the parent, those are ignored. I mean, not really ignored. These are useless because they have to be smaller. So basically, to them, so I don't consider them, right? So we only go with the ones that are smaller than us, and because each one will return how many is starting from this one, and how many is starting with this one. So, like in this case, I start with 1, right? And this is 3. This is 2. Then, but we can start with 3, right? Now change the idea. Largest value have advantage. Follow this thought. Largest value has advantage because if I give a pair of the largest one, then all the paths that can connect those two satisfy. That's correct, right? So why don't we just do that? We find the largest pair and count the number of paths in between them. How do we count the number of paths in between them? I don't know. But we want to count the number of paths in between the largest one, and then we count the number of paths, and then we remove the largest one. Right? We remove the largest one because it's the largest, it's not going to work. Then we count the number of paths in between the second largest one. Okay, but then how do you find the largest one? Well, I know the largest one because I have their values. So I know which one is the largest. I mean, it could only also be like a heap, right? It could be a heap. So I can pop them out and then traverse them. It seems very inefficient. I know it's connected. Wait, hold on. Does that mean there's only one path in between them? I think so. So the biggest two, it's guaranteed that there's only one path between them. If there are two paths between them, then it will have a cycle, right? So if we find the largest one, there's only one path. Then we pop them. The problem is after you pop them, the graph might not be connected anymore. Now you pop them, the graph might not be connected. So the remaining, that is the problem. Yeah, like here, right? If we pop this, this node is basically by itself, right? So we want to know is after we pop in some nodes, who are still connected? Yes, who are still connected? And it will be like however many, choose 2, right? That will be the total number of paths in between. And then when you pop, how do you know if you pop some are not connected anymore? I don't feel. Yeah, I remember the solution is find the largest. I remember that. But then, after the largest is considered, what's the next step? Well, the next step is finding the second largest to sort the values, right? And then we have the largest, we deal with it, and the second largest. But we don't know if the second largest are connected to each other. How can we know that they are connected? Or maybe we can do is retraverse the tree, right? So we remove the edges, which is totally fine. We can turn into a graph, and it could be a node and a set. So once we deal with one, we will remove that, and everybody will remove that. And then we will traverse the whole thing again, traverse the entire graph to see how many who are still within. Okay. So what you're saying? So we'll find the largest, right? And then we'll remove everything. And then we need to group them together. Okay, we can union find. We can union find to group them together, and then find out who they are that's still connected to each other. And then we're going to remove those and then redo the union find to group them again. Hold on. So one more time. So initially they're all connected, right? So we do that. Just for the DSU. Okay. And then we remove those. Basically, everyone that has connection will be removed. Okay. And then we'll build another DSU. And then inside this DSU, we will go through everybody that's still in it. We go through everybody that's still in it. all the nodes that's still in it. And based on their relations, right? Based on their relations. So we have vowels. Okay, so we just use the edges. We use the edges, and then we have another set. And every time I go through the edges, we check if one of them is in it, then this edge does not exist anymore. Right, this set does not exist anymore. And then I don't like it. I don't like it. I think I'll get a graph. I'll get a default dict with a set. So we'll have the values. It's gonna be like a queue, right? So we push the first values in, which is going to be I might as well sort this. Or a heap. A heap. Yes. Yes, it can be a heap. It can be a heap. So we just pick all of them out. Okay. And then we calculate how many paths there are in between them. Right? There's only one path between them. And then we go to the graph, the delete. Right? Delete them. And after we delete everything, we have a new graph. Then we run union find to see who is still with whom. Yeah, we go through this one, and then we'll union these together, and then go to this one, we'll union them together. Go to the next one, there's a union everybody together, and then go through that. Then what? Then I need to know who is together. So we get them together, and that will be a new values, or the new heap, right? We'll create new heaps. I don't really know if heaps is the right one to do this. Maybe as well just sort them. We can heapify and then just I might as well just sort. Reverse sort. Take all those. Okay, I'll give it a shot. It feels kind of slow, but maybe it'll work. Okay, so what are we thinking? We are thinking a graph. Okay. It's okay that if we don't do this. If we don't do this, you know what? Maybe we don't need to do this. If you don't do this, how do you know which one is currently available? We know who is currently available. We'll remove them, so those are the currently available. So we go through these, And if it's not connecting, then we don't have anything for it. You know what? Maybe we don't need it. Maybe we don't need it. Maybe we do not need it. So what we need is the values, right? What we need is the values. Values of everyone that's inside the same connected graph. So what we do is we will sort the values. So I say, hold on, let me Q for IV in numerate vowels, right? We then do value I, rest equals len vowels, right? These are just that, and then while Q current vowels equals for current vowels in Q. Maybe we can index. Okay, while Q current vowel equals dec Q dot pop left. Okay, and then dot sort reverse equals true. Then max current max equals current vowels 0 and 0. Okay, and then and also we need nodes. All right, nodes shall be set range res. You can say current max equals this one. Oh, we don't reverse. We can pop. What would be the best way to do this? Current max in I equals this one dot pop. Right, and then nodes dot remove I. Say while current vowels minus 1 0 is equal to current max. Count equals 0. Count equals 1. Then nodes dot remove current max, current vowel pop 1, count plus equal 1. Back again, back again, back again. While current vowels and so ba 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 ba. Once we're done, we have a count, and rest will plus equal to math.comp count choose 2. Right, and once we're done, we need to produce new. So we'll go through the edges. Okay, we go through the edges and we'll create a new edge. All right, new edge. Hold on, you have a new edge? Yeah, we have a bunch of edges, so we go through them. That doesn't sound nice to me, huh? That doesn't sound nice to me. I think we still need this. Okay, we have the Q, we have this, blah blah blah. Then, we need everybody. Then we don't need nodes because that is inside the graph. We have queue, we have current val, we sort, we get it out, and then there shall be nodes, right? Nodes to remove. We don't need this. We just say nodes to remove dot append. Alright, and then nodes to remove, and this is just going to be len nodes to remove. These are the largest value. Okay, so when this is done, we will go through the graph and deal with them, just to remove them, right? Don't just say for node in nodes to remove graph for each node, right? For child in graph node graph child dot remove node. Done with that. Graph dot del graph node. Okay, so after done this, we clear out the graph. Then, based on what they have, we need to produce a new value list. Basically, we need to know who are still connected to whom. Maybe we can just DFS this. DFS from whatever we start, and then just go through everything, and then what? The path, not the path, visited. Everybody that's visited. Okay, we can DFS, find out hold on. Okay, we need a DFS. I have a node visited. Don't return anything. Oh yeah, we need a graph. Shoot. Alright. If next is not in visited, we need to say visited.add next, add node. If it's not in visited, DFS next visited. Right? And blah blah blah. That's it. That's the DFS. So after we clear up the graph, we need to traverse. But when we traverse the next one, how do you know it has been visited? Good question. We have multiple cliques. Okay, so this, let's call that a clique. click, click. Right? And I will do a global visited. Okay, we can do that. Self.visited equals a set. Every time and self.visited node as well. And next is not in self.visited, we visited. Okay. And every time we say self.visited, clear. I think Python has that. Yep, it has that. So we clear this, and then we can say, say what? If it's not visited, right, we're gonna say for node, for root in graph.keys. Right, these are the roots. If root not in self.visited, then we can say DFS root and the click. That's gonna be the click equals a set. So that's gonna be a click. Right, we DFS this. Once we're done, click will be filled with everything, and then we can say q.append this thing for, holy moly, I only need their, because I can sort based on something else. Holy crap. Yeah. Okay, a deck of, hold on. A deck of what? A deck of lists range. Len vowels. Okay, dot sort key equals lambda a item vowels I. Right? After I sort, when I pop out this, okay, the index needs to remove, we have index. Current while this equals vowels index, and I'm gonna append this. Nodes are remove. Dot append. This one pop, 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 until we finish. This will be this. That is correct. And then for each one of this, I do all this, and then I clear, and then we do this. Now q.append, I have a click, which is everything. So that's just going to be dot append. Or we can actually just append the click. Let's list the click. Right? And then the next one, if it's not in, if it's visited before, we just skip. Skip. If we do this, okay, this is the next one. And then we'll go back up. Alright? We pop out. We do the same thing. Oof, every time is a sort. Damn. Get index until what? Until we are done. int will return rest. All right, let's see. Are you sure? No, I'm not. I'm not sure at all, but take a look. Take a look. Number 6. What's this? 7. This is 1. All right, we'll see if this one works. The chance of it working is very, very slim. But we see. Oopsie doozy. All right, what was wrong? Int object is, oh, of course it's not. Val this. Yeah, I changed the thing halfway. Ooh, look at that. These all pass. Okay, maybe. Well, let's try. Maybe. What do you think? Just run it. Come on. Come on. Do we have it? Oh, take a long time. It's a long time. That's a long time. Yeah, I done the last time. Look, it took so long, right? Last time to solve this. Wait, this is weird. This is taking way too long. This is taking way too long. Either some bug in a submission system. What do we do now? Is the system down? I mean, the contest is happening right now, I think. So maybe we are crashing with a contest. That's fine. Let's refresh. Wrong answer. Eee, ugly. Oh, yeah. Yeah, I remember last time this one was not smooth at all. Expected 11. I got more than 11. All right. Run it. Okay. Let's draw it out. 0 to 1. 2 to 1. 0 to 3. 4 to 1. 4 to 5. 3 to 6. 7 to 5. 2 to 8. Okay. And the value is 2, 4, 1, 2, 2, 5, 3, 4, and 4 have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9. The answer says 11, so we only have 2 more. I said 17. Jesus. I said 17. Wait, hold on. I said 17. I did this combinations, right? What's 1? Let's see, 1 choose 2. 1 choose 2 should be 0, right? 1 choose 2. That's math error. Nodes to remove. Well, I never have this. Because 2 choose 2 is 1. Okay, let's see. So we find the largest value, which is 5, right? So initially, coming in, nodes to remove is 5, and then nothing. And then, wait, you can do 1 choose 2? It gives you 0, which is fine. What I think, no, you don't think. You do not think. So initially 5, so 5 is gone, which takes away all those. Right, 5 is gone, so we have 7 by itself. and then the remaining. So now it's gonna be 4. Yeah, let's print out. Let's print out the current values every single time. Okay, let's print that out. Kind of see if it's right. So we print current vals. Oh, what the hell? This one repeated so many times. 0 and 3. Wait, what? That doesn't seem right. Okay, that's the first, right? It's the second. We remove 5 and 7. Okay, this is 7. So among this, 4 is the largest, right? And then if we take 4, we have 1, 2, so it's 1, right? And then we remove them. If we remove these, what we get, so remove this, is 0, 3, so 0, 3, 6, which I got a 0, 3, 6. That is correct. We have 0, 3, 6. And 0, 3, 6, we got 0, 3, right? And then we'll have 0, 3, 6, we'll have 2, 4, 7. That's correct. And 2, 4, 7 are all gone. Are all gone. In fact, the 2, 4, 7 all go through this thing. We can sort. That's fine. This is no. This will be 0. That will be 1. We do need this. And graph.keys. Oh, I think I know what happens. It just goes through too many times. Okay. Okay, this is correct. It's just they're on the same level, right? Hold on. Think about it one more time. So we remove those, right? Once we remove it, and then we split it into separate subcontinents, basically. Then the search shall be within the subcontinents. Right? Hold on. One more time. We find the largest one, and we take the largest one away, right? Then we have the remaining ones. And the remaining ones, we only need to do that once. Okay? We shall only do that once. But now I'm doing it multiple times. And the reason I do it multiple times because if I do this, I have all of them are at the same level. Right? All of them are at the same level. So this can produce. Oh, how do I handle this? Hold on. So when I remove these, I produce the next level of things, right? And then when the next level comes in, this one will remove some stuff. And I shall traverse within that, which means it's not for root in graph keys. It should be for root in what? In the remaining things, current vowels. Hold on. So first of all, this is not current vowels. Okay? I would say current nodes. These are nodes, right? So current nodes, I think it should be for root in current nodes. Root in current nodes, because current nodes is its own click, right? Its own click. And within the current nodes, we try to see if we can split into even further ones. And every single time that we do this, and we do DFS, and now they remove it, so we don't do anything. Hold on, let's try this one. This one pass. You see that? This one pass. So it has to go through its own click. Doesn't go through the remaining. Okay? Okay? One more time. One more time. That's okay. That's okay. Look at the previous track record. It's a tough problem for me. Okay. Let's see. Let's see. Damn it. It took so long. So either timeout or what happened today? Like seriously, what happened today? Oh, here we go. Time limit. Ah, dang it. Okay, so it's right. Right? It's correct, but damn. 11 test cases left. Is this one like fail by itself? Just curious. Are we redoing stuff? Yeah, I mean, every single time I have to traverse everything. But this traversal is on. Yeah, so every time is on. Every time it's on. I don't know, man. What if I just remove? I don't go through all the child to remove. If I just remove that node from graph. If I just remove that node from graph. And then we put those in the visited. Then we go through. Hold on. What if I do that? So I don't go through this. I just go through this. Right? Self.visited equals set nodes to remove. Nope, nope, nope. That's not right. Why? Why would it not be right? Why? Yep, it's all right. I just didn't delete it. I didn't remove it from the child. What do you want to do? I have no idea. You think it's a sort? I don't think it's a sort. Sort shall be fast. It's the traversal again is slow. Maybe we can do. We can try union find. Right, we have who to remove. No idea. No idea whatsoever. I mean, I can try union find. You wanna try? Man, why not? I mean, we're already here. This is not working. This is but I think the idea works, but union find. We just want to find. I mean, try union find for finding the click, I guess. For that, then I don't need this, right? I don't need DFS. I just need union find. Okay, let's do DSU. I mean, we are in this union find thing. Maybe this one is still union find. So our parent is going to be range n, and self.rank going to be 0 times n. Find x int if self.parent x is not equal to x, self.parent x equal to self.find self.parent x return self.parent x union be x and y. Okay, don't make the mistake. Parent x, parent y is going to be find x, find y. Okay, if we don't return this, we return boolean value. If px is equal to py, then we say false. We don't union. Otherwise, if px, if self.rank, px is larger than self.rank, py, then self.parent py equal to px. Now if self.rank py is larger than self.rank px, then self.parent px equals py. Otherwise, we say self.rank px plus equal 1 and self.parent py is equal to px, and we return true. Okay, so the union find, so everything else is the same. This is the same. This I want it to be the same. This, so this is just pick the last. Maybe an easier way than doing it this way. Yeah, why do you do it this way? Why do you do it this way? Yeah, why do you do it this way? You can say for I in range 1 to len current nodes, if vals I is not equal to vals I minus 1, right? Then we break. So whatever I is going to be the difference, right? We can actually call it count, right? For count minus 1, to come out is going to be the count. We don't need this. We don't need this. We don't need any of this. We don't need any of this. So we can just say this is a count. And then we do need to remove. So for node in, not node, for I in range count. Node equals current nodes I. We do this, we do this, we do this, right? And then we don't do this. Now we can use the DSU. Now how do we use the DSU? We have the nodes, right? We have the current nodes, and we need an n. We do need an n. Len vals. Okay, we do need the n. And then we create a DSU, And then we go through all these nodes, and then, okay, so we say DSU equals DSU n, okay, then we say for node, actually because I sorted already, so just the remaining, right? So for node, no, for I in range, count to len current nodes, node equals current nodes I, right? Then we go through the graph, then we say for child in graph node dsu.union node and child, right? We'll go through all of these. Then we want to know who are together, right? We want to know who are together. So how do we do that? We need to find a parent. Oh my god, this is getting more and more complicated. Clicks, by default dict a list, and then for, oh my god, this is not happening. Hold on. We can do it this way. No, because we need to, after union everything, then we do it again. My god. And then we do it again. Okay, so we union everything, right? Then we do it again. For each node, we're gonna say clicks DSU, right, dot find node, okay, dot append node. Done. Then we say for Lord, for v in clicks dot values, if len v is larger than 1, then q dot append list v. I mean, v is already a list, so we don't have to list v. We just append this. Okay, how about this? This is one we'll... Solution 2. It's not right. Oh my god, this one's not right to begin with. How? Doesn't matter. Calm down. We just print this out and see what goes wrong. Okay, let's go back here. First one's everything, and then remove the largest, should be 0 to 3. 0 to 3. What the hell is 4 doing there? And then 2, 0, 3. That is not... Hold up. Let's print this and print count. Count is 1. That's bonkers. Count is 1, right? And 1. Oh, vowels. No. Count. That's not right. It's current nodes count. Current nodes count. Now we're good. How about you guys? Huh? What happened here? Which one? Oh, I bet it's this one. Yep. 0 by itself. And to prevent that from happening, we can prevent here. But here we do not prevent. So we should prevent it from here. We can do this one at the beginning. If n is equal to 1, return 1. Just, sanity check. Then this one pass. Meh. And we failed the last one. No, we failed multiple. Alright, what's wrong with this one? Okay, so this one, that count as 1 again? What? I have 4 and 2. That's bonkers. 4, 2, no. Oh wait, 4, 2 is right. So this is 3. My bad. So this is right. And then count is 1. This will be 0. So it'll be 0. And then current node. Yes. So we'll remove this. DSU. For I and count as 1. Length current node. So 2, 3, 0, 1. We do this. Click. So next one is 2, 3, 0, 1. That's correct. 2, 3, 0, 1. Count as 2. So we will add 1. The next one is 0, 1. Alright, the last one is 0, 1. 0, 1. We have a problem here. Is equal to, it doesn't go up. Oh, Jesus. There we go. All right, try our luck. This is a DSU kind of solution. So we have better luck with this. Tough luck. I think this one's time out as well. Oh. Lordy. Hint. It's the union find. I'm doing the union find wrong. I mean, do we have clear? Can we ununion? How do we ununion? I mean, it's all linked to the start. So if we ununion this one, yeah, you can, because they all path compressed. I do not know if there is any way to ununion. I mean, I know the general thought, right? The general thought is to create cliques, but this is one way to build cliques. How do you ununion? Ununion. So everyone who has a connection to this node. So it's like, say, these two nodes have connection, right? If they do have connection, then now we see the connection is broken now. So if the connection is broken, they shall both pointing back to themselves. But then in this one, I shall go, nah, I don't know. I have to see the hints. Okay, I know this. I know this. Oh, smallest value to the largest. I'm trying from the largest value to the smallest. Now it rings more bell from the smallest value to the largest. From the smallest value to the largest. Hold up. So if I go the smallest, right? So I have the smallest, and then we find the next smallest, and what? I have the smallest, the next smallest, try to build a graph from nodes with the smallest to the largest. Smallest. Wow, I look great. Smallest value, okay. And then this one is connected to this, so we can union them together. Okay. This one union with this one union with this. Okay, next one. So once we find, I don't know, smallest value. Well, if the smallest value, they do not connect directly, then it's a no-go, right? So we can find the smallest nodes, okay? We start with the smallest nodes, we look around, and none of those are small, so these are no-goes. So now we need to look the second smallest. Okay. And the second smallest.
That was another bagel name.
Ralph.
Scout, Ralph, Benny.
Wow, your memory is coming back.
Name started with a P, I think. I don't know.
Penny.
No. I thought that too.
Pixel.
No.
That's phone. Yeah, the good part is we don't have to remove, right? We just need to add. How do we do that? Step in.
No, that was a pig.
We pick the smallest first. And then, well, they're not connected, right? The smallest are not connected, so that's bad. Now we pick the second smallest. Okay, now I'm in the second smallest. We try to connect with the ones that's only smaller than me. Oh, okay. What is that? If you are the smallest, whatever the value you are, you're your child. You only pick the one that's smaller than you. Then you will create whatever graph you have, right? And then you look to the next one. You try it again. And once you've done that, you try to see, right? So I have mine, and we try to, that was the first one. Okay. Then we see, we see if the two are the same. If they're the same, that means they're in the same clique. And then with the next one. I think I might have an idea. Hold on. All right. Trial number 3. Trial number 3. Union find again. But this time we start from smallest to biggest. From small to big. And build only one union find, one DSU. Okay, at each node we only add edges leading to children, right, that have values smaller than us. Okay, so we start with the same, and the rest is the same. DSU equals DSU and we're gonna sort vowels, not vowels, nodes. Dot sort. Okay. Sort the nodes. Then for each one, okay, for node in nodes. He didn't even say what nodes is. Sorted range n key equals this. Okay. Now for each node, I look around. Okay. Then for child in graph node, I look around. If vowels child is smaller or equal to vowels node, then DSU dot union child node and child. Okay. So blah blah blah. When we're done, we want to know the previous, right? We want to know the previous, which means I want I node in enumerate. Okay. So once we're done, I want to say if vowels node. Oh, that's not good. Nodes. It's okay. That's okay. Is vowels node if I is larger than 0 and vowels node is equal to vowels nodes I minus 1, right? If these two are the same, then we need to know if these two belong to the same clique, right? If they belong to the same clique, then we can create a path. Okay, but what if we have another one? What if we have another one? Current value. Count. Hold up. So we need a current value. Okay, current val. Current val is -1. And count is equal to 0. Okay. So blah 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 blah. And then we say if vowels node, right? If that is not equal to current val, then whatever count we have then whatever count within the rest plus equal to mass.combination whatever count, pick 2. And then after that, count equal 1. This is the current one. Right? Actually, we can start with 1. Doesn't matter which you start with. Right? If it's not equal to. And then current val will equal to vowels node. Else, if the two values are the same, then if the two values are the same, right? So the current val and the previous are the same, then, but what if what if hold up. We record the current val. Okay. So if it's not the same, we'll do count. If not the same. If it's not the same, hold on. So we have the current child, right? If it's the same, we just keep going. And then the next one, the value is not the same. So before I union, okay? Before I union, if it's not the same, we need to, okay, if I is larger than 0 and before I union, if I is larger than 0 and the current val is not equal to the previous val. So if that is the case, then I need to go through all the previous, right? So I need to say j equals I minus 1, right? And we say while j is larger than or equal to 0, so we go through all of them to find how many of them have the same. Or get their parents, right? While j larger than or equal to 0 and vowels node j, sorry, yeah, is equal to current vowel. Counter. DSU find node j plus equal 1. J minus equal 1. Okay. Once we're done, say rest plus equal to sum for v in counter dot values mass dot combination v2. Once we're done, current value equals this, update it, and then we do this. Then we go up, then we go up, then we go up. And then return. Loop. Nodes. Almost. Oh, this will be hard to debug. So we start from the 1, right? No, 0 and 1. No, wait, no, it's this one. We start with 0 and or 3, doesn't matter. We look around, right? Because I know I is equal to 0. So if a child in graph, let's say we handle this one first, child. If I's child is smaller than 0, so we don't do anything. Next one come in is this one, and I is larger than 0. Vowels node is 3, is not equal, no, vowels node is 1, it's not equal to current vowel. So I equals, j equals 0. Okay, and then j larger than 0, and this is equal to, no, it's not equal to, so we don't do anything. So this is still gonna be 0, but current vowel will equal to 1. Okay, current value equal to 1. And then we'll connect this. Nothing. Next one come up with 2. 2 is not equal to the previous. So try to go in. Previous one is equal to. Still 0, I should be. And now we'll call it this. This. We don't include this. Finally, we add this. And I see the problem. I think we should add the child. We add them. Next one, we add them. And once we got something, well, yeah, because in this case, these two are never together. So you say every time we add them, okay? But every time if we add them, they're already connected. No, we don't add them. I think it's the reason is the last one coming in. Because the previous vowel is 2, right? So when the last one comes in, no, the previous vowel is 3, so they are the same, right? And when they're the same, we don't do anything. We make the connection. So we need to handle it one more time. Ugh. So how to do this one more time? Handle the last vowel. There we go. Yep, that's the last one. All right, try this. Boys and girls, let's try this. Keep pending. My God, come on. Is a contest about to end, or it's just a lot of people there? Oh, too many people submit. Look at this. I got temporarily rate limited. Yeah, I think it's maybe the contest about to end. 4 a.m. UTC. Yeah, contest just ended. A lot of people submitted last minute. Oopsie doozy. We picked the wrong time to do this.
That's my alarm clock, right? This one?
Which one?
No.
No, not this one. LeetCode is broken. Too many people is using the site. The traffic is down.
I know.
Because the contest just ended 10 minutes ago. I think probably been down for 10 minutes.
When is it supposed to end?
It's supposed to end 8 o'clock. 8 p.m.
8:12.
Yeah, it just ended.
Oh, so it's supposed to end 12 minutes ago.
I think it did end 12 minutes ago. But
How's that broken if it's supposed to finish at 8?
I'm not doing the contest. I'm trying to submit a solution for another problem, but I got rate limited. I got error, and I cannot load LeetCode's page anymore. So I think
What does it have to do with the contest then?
at the end of the contest, a lot of people submit. I think the traffic overloads their server, so their server has been down.
Contest ended at 8?
Contest ended at 8. So I think they've probably been down for 10 minutes. They're using Cloudflare. That's the one. Wait, that's the timer. Well, this is the first time that happened. I don't know, man. Should I end this? I mean, it's already 1 hour and a half, so I should probably end this. Man, we've done this before, but we still struggle. I think this one should be right. We're building from ground up. We literally build from ground up. So I think this one shall be right. But I just cannot load it. I'll end it. I'll end it right now. I have confidence that this one will work. All right, now I'll see you guys tomorrow. Adios.